Good evening. Welcome to the channel where the bustle of the day dissolves into the evening twilight. Tonight, we are traveling millions of years into the past, to a time when dinosaurs ruled the world. Let us begin. Imagine finding yourself in a Cretaceous forest, not beside a Tyrannosaurus, not in the middle of a herd of Triceratops, just among the trees. For the first few minutes, there may not be a single large animal anywhere around you. And yet, almost immediately, an unsettling feeling would arise. This is Earth, but it does not belong to you. The forest would seem familiar and wrong at the same time. There would be ferns, conifers, cycads, and ginkgos. You would recognize some forms, while others would resemble no modern plant you know. Flowering plants had already appeared and were spreading rapidly, but the familiar landscape of meadows, fields, and thick carpets of grass did not yet exist. Even trees that looked familiar formed unfamiliar communities. This is not a modern forest into which an artist has placed dinosaurs. It is an independent biosphere, assembled according to different rules. And before we go any further, check that you are subscribed to the channel. If you have not subscribed yet, be sure to do so you do not miss new facts, stories, and myths about our world. Let us continue. It is important to get rid of one misconception. The age of dinosaurs was not a single moment in time. The Mesozoic lasted for more than 180 million years. That span is so vast that Tyrannosaurus lived closer to us than it did to Stegosaurus. The Triassic world of the first dinosaurs, the Jurassic ecosystems of giant sauropods, and the forests of the late Cretaceous differed from one another as profoundly as separate chapters in the history of the planet itself. During the Triassic, almost all land was joined in Pangaea, an enormous continent stretching across climatic zones. Its interior was dry and subject to sharp seasonal fluctuations. Later, Pangaea began to break apart. During the Jurassic, northern Laurasia separated from southern Gondwana, the Atlantic Ocean opened, and the outlines of the land slowly began to resemble a very distant version of the modern map. But only distantly. A person still would not recognize the planet from its coastlines. During the late Cretaceous, a shallow sea cut across North America from the Arctic almost to the Gulf of Mexico. Ammonites, sharks, and enormous marine reptiles swam where plains and agricultural states lie today. At certain times, sea level stood roughly 170 meters above its present position, allowing water to penetrate far into the continents and create vast, warm seas. Reconstructions by the Natural History Museum in London confirm these features of Cretaceous geography. The climate was different as well. For much of the Mesozoic, Earth was considerably warmer than it is today. Stable polar ice caps did not exist, and forests grew at latitudes now covered by Antarctic ice. That does not mean the same tropical heat prevailed everywhere. There were arid regions, humid coasts, seasonal forests, river valleys, and cool polar areas. Even so, the entire climate system operated in a warmer state. Changes to the map affected almost everything. Continents breaking apart divided populations. New seas blocked migration routes. Where the water retreated, plains and wetlands appeared. Vegetation changed, followed first by herbivore communities and then by predators. Dinosaurs did not merely live against a backdrop of geological events. Their diversity was, to a great extent, a product of those events. A person transported to the Mesozoic would therefore probably notice something other than a dinosaur first. They would feel the heat, see an unfamiliar forest, search in vain for familiar birds overhead, try to make sense of the strange coastline, and only then hear something heavy moving between the trunks. That is the essential shift in perspective. Dinosaurs were extraordinary animals, but the world around them was no less extraordinary. To understand why they became so enormous, diverse, and successful, we must first understand how this alien Earth actually worked. We have already seen that Mesozoic Earth bore little resemblance to the modern world. Now we need to make another correction, a temporal one. And it is fundamental. The phrase "age of dinosaurs" makes it sound as though we are discussing one long period with roughly the same climate, vegetation, and collection of animals, as if Stegosaurus, Tyrannosaurus, and the first small dinosaurs all lived somewhere near one another and simply did not always appear in the same frame. That is wrong. Non-avian dinosaurs existed from approximately 245 to 66 million years ago. That gives us almost 180 million years of evolutionary history. By comparison, the entire history of humanity occupies only a barely visible section at the very edge of that scale. Even if we begin with the appearance of the first members of the genus Homo, we get only a few million years. Here, however, tens of millions of years separate worlds that we habitually compress into a single image. The best-known comparison sounds almost like a historical provocation. Tyrannosaurus lived closer in time to modern humans than to Stegosaurus. Around 66 million years separate the last tyrannosaurs from us. Stegosaurs, however, disappeared roughly 80 million years before Tyrannosaurus appeared. In other words, to Tyrannosaurus, the Jurassic world of Stegosaurus would have been an antiquity as deep as Tyrannosaurus seems to us. The Mesozoic must, therefore, be divided into at least 3 broad pictures, not so that we can memorize a geological table, but so that we stop placing side by side animals and events that were actually separated by immense spans of time. The first picture is the Triassic. It began around 252 million years ago, shortly after the greatest mass extinction in Earth's history. The biosphere was recovering from catastrophe, and dinosaurs did not emerge into a finished world that immediately belonged to them. At first, they were merely one of several developing groups of reptiles, and looked nothing like the undisputed rulers of the land. Almost all the continents were joined in Pangaea. This enormous landmass extended nearly from one pole to the other, and its interior lay far from the ocean. That intensified the continental climate. Hot seasons could give way to cooler ones, and wet periods to prolonged drought. Much of Pangaea consisted of dry plains, semi-deserts, and deserts. Other regions experienced powerful seasonal monsoons, so the entire Triassic cannot be described simply as arid. Still, the overall conditions were harsh: high temperatures, scarce water, and abrupt seasonal shifts. The first dinosaurs fitted this world. Most were relatively small, agile animals, and many walked on 2 legs. Alongside them lived large amphibians, early relatives of crocodiles, herbivorous synapsids, and other creatures that are almost absent from popular culture today. If we could see a late Triassic ecosystem, we would not immediately realize that the famous Age of Dinosaurs had begun. Dinosaurs were not yet the main characters. They were only entering the story. At the end of the Triassic, the planet experienced another mass extinction. The disappearance of many competing groups opened ecological niches, the places and roles organisms occupy within ecosystems. Dinosaurs gained room to spread further. This brings us to the second picture, the Jurassic period. The Jurassic began roughly 201 million years ago. Pangaea was already breaking apart. Laurasia was forming in the north and Gondwana in the south. Seas were widening between the great landmasses, and the Atlantic Ocean was only beginning to open. The fracturing of the continent changed atmospheric circulation, the distribution of rainfall, and the very routes by which animals could disperse. In many regions, the climate became wetter. Forests, dominated by conifers, cycads, ginkgos, and ferns, expanded. Flowering plants did not yet exist, which meant there was none of the familiar modern abundance of flowers, fruit, and broad-leaved forests. But there was enough plant biomass to support an entirely new scale of life on land. The Jurassic became the age in which giant sauropods, the long-necked herbivorous dinosaurs, flourished. Diplodocus, Brachiosaurus, and their relatives became the largest land animals ever to exist on the planet. Stegosaurs, large predatory theropods, and many less familiar forms lived alongside them. It is important not to replace an explanation with an appealing myth. The gigantism of Jurassic dinosaurs cannot be reduced to a single cause. such as supposedly extraordinary levels of oxygen. A combination of factors was at work: the structure of the respiratory system, rapid growth, skeletal anatomy, reproductive strategy, the availability of plant food, and the organization of the ecosystems themselves. An enormous body did not arise by accident. Evolution made it possible, and under certain conditions it became advantageous. Yet the Jurassic world was not permanent either. The continents continued to separate, the oceans widened, and coastlines changed. Around 145 million years ago, the Cretaceous began, the longest period of the Mesozoic and the third picture on our timeline. By then, the single stage was finally breaking into separate regions. North America, Asia, Europe, Africa, South America, India, Australia, and Antarctica were gradually taking on distinct outlines, although their positions still differed greatly from those of today. Geographic isolation intensified. Populations that had once been able to meet were separated by seas and oceans. Isolation is one of the most powerful engines of evolution, and different parts of the planet developed their own dinosaur lineages adapted to local conditions. Sea level remained high. Shallow basins flooded large parts of the continents and divided the land into separate territories. The climate was generally warm, although it changed repeatedly over the nearly 80 million years of the Cretaceous. The early Cretaceous, and the final few million years before the catastrophe, were therefore not the same setting either. The greatest biological transformation was taking place literally beneath the dinosaurs' feet. Flowering plants, which had appeared earlier, began to spread and diversify rapidly during the middle of the Cretaceous. Insects, food chains, and the structure of terrestrial communities changed with them. New kinds of plant food appeared, while older plant groups lost their former undisputed dominance. The ecosystem was becoming different, and dinosaurs had to change with it. Many animals now regarded as symbols of the entire Mesozoic appeared during the Cretaceous: horned ceratopsians, duck-billed hadrosaurs, later forms of ankylosaurs and tyrannosaurids. But even they did not all exist at the same time. Tyrannosaurus itself appeared only at the very end of this immense history, and lived on Earth for a relatively short time, roughly the final 2 million years of the Cretaceous. It was not the eternal king of the dinosaurs. It was one of the last great predators in a world already approaching its boundary. The Triassic, Jurassic, and Cretaceous, then, are not three convenient names for a single landscape. During the Triassic, dinosaurs arose on hot Pangaea and long remained only one part of a complex community. In the Jurassic, the breakup of the supercontinent accompanied the expansion of forests and the flourishing of true terrestrial giants. In the Cretaceous, the continents moved farther apart. Seas penetrated deep into the land, flowering plants began to reshape ecosystems, and isolated populations produced many new forms. What matters here is not a list of dates, but a rule. Before imagining two dinosaurs beside one another, we need to ask three questions. When did they live? On which continent? And in what ecosystem? Without that, the Mesozoic becomes a beautiful but false stage set. With that understanding, it begins to look as it truly was, a constantly changing planet where animal evolution followed the movement of continents, shifts in climate, and the complete reorganization of the living world. Now that we have put time in order, we need to do the same with names. Popular culture treats the Mesozoic rather casually. If an animal is ancient, large, scaly, and dangerous-looking, it is almost automatically called a dinosaur. That may be enough for a film. It is not enough for understanding the real world. Dinosaur is not a general name for all prehistoric reptiles. It refers to a specific evolutionary group with its own organized and set of anatomical traits. Size settles nothing. An enormous animal might have no direct connection to dinosaurs, while a creature the size of a pigeon could be a genuine dinosaur. The main history of this group unfolded on land. Dinosaurs belonged to the archosaurs, a major branch of reptiles that also includes crocodilians, pterosaurs, and birds. But belonging to the archosaurs does not make an animal a dinosaur. A crocodile is an archosaur, but not a dinosaur. A pterosaur is an archosaur as well, but belongs to a different evolutionary lineage. One important anatomical distinction of dinosaurs concerns the position of their limbs. In many early reptiles, the legs extended out from the sides of the body, which seemed to sag between them. In dinosaurs, the limbs stood directly beneath the body. This posture supported weight more efficiently, enabled sustained movement, and eventually allowed a vast range of sizes, from small bipeds to multi-ton giants. But looking at the legs alone is not enough to draw an exact boundary. Modern systematics is based primarily on relationships. It uses the concept of a clade, a group comprising a common ancestor and all of its descendants. Dinosaurs form such a group. That is why a dinosaur cannot be defined simply as a large ancient lizard. We need to know which branch of the evolutionary tree it belonged to. Let us begin with the sky. Pteranodon, Rhamphorhynchus, and the giant Quetzalcoatlus often appear beside dinosaurs in books and films. They did indeed live during the same era, and some shared ecosystems with dinosaurs. But they were not dinosaurs themselves. They were pterosaurs, a separate lineage of flying archosaurs. Their wing was supported by a greatly elongated fourth finger, with a membrane of skin stretched between it and the body. The structure of a bird's wing is entirely different. Pterosaurs were the first vertebrates to evolve powered, flapping flight, long before birds appeared, and they survived for more than 150 million years. Yet close proximity and a distant common ancestor do not make them dinosaurs. The same confusion surrounds the seas. It is easy to mistake an ichthyosaur for an ancient marine dinosaur, a large body, a long snout, and reptilian origins. In reality, ichthyosaurs were an independent group of marine reptiles. Their streamlined shape resembled that of modern dolphins to a remarkable degree, although the two were not closely related. This is an example of convergent evolution, a situation in which unrelated animals independently acquire similar traits because they are solving the same problem. A particular body shape is efficient for moving rapidly through water, and evolution has repeatedly arrived at a similar solution. Plesiosaurs, with broad bodies, 4 powerful flippers, and sometimes extraordinarily long necks, were not dinosaurs either. They belonged to another branch of marine reptiles. Mosasaurs, which appeared much later, were relatives of lizards and snakes. None of these animals became marine creatures by evolving from a terrestrial dinosaur. This is an important distinction. Many large reptiles lived in Mesozoic seas, but there were no marine dinosaurs in the usual sense. Some dinosaurs entered the water, hunted in the shallows, or were closely associated with aquatic habitats. Spinosaurus, for example, possessed pronounced adaptations for a semi-aquatic way of life. But there is a major difference between an animal that swims well and finds food in water and a fully marine evolutionary lineage. The picture is straightforward. Different groups of dinosaurs dominated the land. For a long time, the air belonged chiefly to pterosaurs, and later birds appeared alongside them. Ichthyosaurs, plesiosaurs, mosasaurs, and other reptiles that were not dinosaurs lived in the seas. These animals existed at the same time, interacted, and sometimes preyed on one another, but they belonged to different branches of evolution. And here we reach the most important clarification. Dinosaurs did not disappear completely. Birds are not merely distant descendants of dinosaurs, nor are they a separate group that once evolved from dinosaurs and then ceased to be part of them. In modern systematics, birds are living dinosaurs. More precisely, they are the only surviving lineage of theropods, the major branch that included many bipedal predatory dinosaurs. This is not a poetic metaphor or an attempt to make the sparrow seem more impressive. The relationship is confirmed by skeletal anatomy, the respiratory system, the structure of the limbs, reproductive biology, and an enormous fossil record. Feathers did not suddenly appear with the first true birds either. They existed in many non-avian dinosaurs and may initially have served for insulation, display, and other functions. Flight came later, when existing structures began to be used in a new way. The statement that the dinosaurs became extinct 66 million years ago, therefore, needs qualification. All non-avian dinosaurs disappeared at that time. One small feathered lineage survived the catastrophe, continued to evolve, and eventually gave rise to the modern diversity of birds. Today, there are thousands of bird species. They live in forests, deserts, cities, along ocean coasts, and even in Antarctica. We see dinosaurs every day. Their modern appearance is simply too familiar to evoke the old sense of scale. The boundary is now clear. A pterosaur in the sky is not a dinosaur. A plesiosaur or mosasaur in the sea is not a dinosaur. A crocodile is a close relative within the broader archosaur branch, but it is not a dinosaur either. The bird outside the window, however, is a dinosaur, and the only one among all those listed whose lineage still survives. Now that the boundary has been drawn, and we understand which animals should actually be called dinosaurs, another question arises. How did this particular branch of archosaurs manage to occupy nearly all the major terrestrial ecological niches? Why did it become the dominant force on land for tens of millions of years? The most convenient answer is that dinosaurs were simply better from the beginning. They moved faster, breathed more efficiently, and grew more rapidly, so they inevitably defeated their competitors. There is an attractive logic to this version. It turns evolution into a contest in which the strongest moves ahead and receives the planet as a prize. The problem is that the fossil record reveals a far more complicated story. We need to begin not with dinosaurs, but with the world they entered. Around 252 million years ago, the Permian period came to an end. Its closing chapter brought the greatest known mass extinction. The overwhelming majority of marine species vanished. Terrestrial vertebrates suffered severe losses, and forest communities collapsed. Ecosystems did not merely lose individual animals, they lost their internal structure. Recovery took millions of years, and it was not a calm return to the old order. Different groups of organisms began to occupy the vacant ecological niches, with archosaurs and their closest relatives developing particularly rapidly. To recap briefly, archosaurs are a major evolutionary branch that includes dinosaurs, pterosaurs, crocodilians, and numerous groups that have disappeared completely. During the Triassic, this branch was far more diverse than it is today. There were armored herbivores resembling a bizarre mixture of crocodile and armadillo. Phytosaurs hunted in rivers. They looked like crocodiles but belonged to a different lineage. Large predators from the crocodilian branch of the archosaurs roamed the land. Some walked on four legs, while others could rise onto two. They occupied roles that would later pass to large predatory dinosaurs. It was on this crowded stage that the first dinosaurs appeared. They were neither gigantic nor numerous, and they looked nothing like the future rulers of the continents. The precise time and place of their origin are still debated. Some finds suggest that animals close to dinosaurs existed as early as 245 million years ago. The first undisputed dinosaurs, however, appear later in the fossil record, around 230 million years ago. Particularly important remains have been found in South America, which was then part of Pangaea. Early forms included Herrerasaurus and Eoraptor. They differed in anatomy and way of life, but neither resembled the giants of the Jurassic and Cretaceous. Eoraptor was around 1.5 meters long and weighed relatively little. Herrerasaurus was larger and was a formidable predator, yet even it did not dominate the entire ecosystem. Most early dinosaurs had relatively light bodies and walked on their hind limbs. The upright position of the legs beneath the torso made movement more economical. Their respiratory systems probably already possessed features that would later reach their greatest development in birds. Rapid growth and an active metabolism may also have provided advantages. All of that matters. But an advantage is not the same thing as dominance. In late Triassic deposits, dinosaurs often account for only a small proportion of the vertebrates discovered. In some regions, they gradually became more prominent. In others, they remained rare. Nor did they spread evenly across Pangaea. Climatic barriers, especially the extensive arid zones around the equator, may long have prevented some groups from dispersing between north and south. In other words, dinosaurs did not burst into the Triassic world and displace everyone else within a few million years. They lived beside powerful competitors and occupied a limited range of niches. Some lineages prospered, while others disappeared. Their future dominance was never guaranteed. It is easy to fall into the trap of hindsight here. We know how the story ended, so its early phase looks like the beginning of a triumph that was always destined to happen. Evolution, however, does not know the future. To an observer in the late Triassic, the large members of the crocodilian branch of the archosaurs might have seemed far more reliable candidates for future dominance. They were diverse, numerous, and already occupied some of the most important positions in terrestrial ecosystems. Dinosaurs certainly possessed a fortunate combination of traits, yet that alone might not have been enough. The world had to change in a way that destroyed the existing balance of power. And it did. Around 201 million years ago, at the boundary between the Triassic and Jurassic, a new global crisis began. Pangaea was breaking apart, and colossal eruptions were taking place in the region that would become the Atlantic Ocean. They created the Central Atlantic Magmatic Province, an enormous expanse of volcanic rock whose traces are now found on several continents. This was not one volcano or one brief eruption. During several pulses, immense volumes of lava reached the surface, while carbon dioxide, sulfur compounds, and other substances entered the atmosphere. The climate underwent a series of abrupt fluctuations. Short-term cooling may have been followed by intense warming. The oceans became more acidic, the carbon cycle changed, and the stability of both terrestrial and marine ecosystems was disrupted. The causes and precise sequence of events are still being refined, but the connection between this volcanism and the mass extinction is regarded as the leading scientific explanation. Many marine organisms disappeared. On land, large amphibians and several successful archosaur groups that had previously occupied important ecological positions were hit hard. The diversity of many members of the crocodilian lineage declined especially sharply. Dinosaurs survived the crisis better than a substantial proportion of their competitors. Why them? There is no single proven explanation. Their more efficient respiratory system may have helped. The ability to maintain a relatively high level of activity probably played a part. Feathers or similar coverings may have protected some dinosaurs from temperature swings, particularly in the cool, high latitudes. The small size of early forms reduced their food requirements. Their rate of growth may have mattered as well, but scientific precision is essential here. We see the outcome of selection much more clearly than we see the mechanism of survival itself. We cannot choose one trait and declare it the universal secret of success. Mass extinctions do not operate like examinations with requirements announced in advance. They alter climate, vegetation, food chains, and habitat availability at the same time. An animal may survive one blow only to disappear because of the next. After the crisis, dinosaurs found themselves in a world where many former rivals had either vanished completely or lost much of their previous diversity. Niches for large terrestrial predators and herbivores stood open. Competition declined. There was room for evolutionary experimentation. That was when their true rise began. During the early Jurassic, dinosaurs spread rapidly and became the principal large vertebrates on land. Predatory theropods increased in size and adopted different hunting strategies. Herbivorous lineages changed as well. Large forms emerged that could process immense quantities of plant food. The ancestors of the future giant sauropods became multi-ton animals with long necks and massive bodies. The term adaptive radiation is especially appropriate here. It means the rapid divergence of one group into many forms, each occupying its own ecological niche. Once their competitors had disappeared, dinosaurs gained access to resources that had previously been divided among different animal lineages. Evolution began to fill the empty space. Even this, however, should not be imagined as an instant conquest of the world. Tens of millions of years separated the appearance of the first dinosaurs from their confident dominance. For most of the Triassic, they remained only one of several successful groups. Their rise resulted from the combination of their own biological characteristics and a global crisis that eliminated a substantial share of their competitors. That distinction is fundamental. If we say that dinosaurs simply proved superior to every other animal, we get a convenient but overly simplistic story. Evolution does not arrange living organisms on a scale from worst to best. It operates under specific conditions. A trait that is advantageous in one world may become useless or even dangerous in another. The Triassic competitors of dinosaurs were not evolutionary failures. Many flourished for tens of millions of years and were superbly suited to their environments. They disappeared not because they necessarily lost a direct struggle with dinosaurs, but because conditions changed faster and more severely than they could withstand. Dinosaurs survived that turning point and then took advantage of its consequences. That was the essence of their success. Their story began not with a crown, but with a place at the margins of a complex Triassic world. Only after the mass extinction did they have the opportunity to occupy the territories and roles left vacant. Chance opened the door, but an accumulated set of adaptations allowed dinosaurs to walk through it. The answer to the central question, therefore, comes down to neither obvious superiority nor pure luck. Circumstances helped the dinosaurs, but only a group that already possessed substantial evolutionary potential could exploit those circumstances. The catastrophe removed many rivals. Everything else, the dinosaurs achieved themselves. Mass extinction cleared the dinosaurs' path, but that explains only the moment of their rise. To understand the next 100 million years and more, we need to look deeper, at the planet itself. Earth was not a motionless stage across which different species moved. It continually rebuilt the stage, altered the climate, cut continents apart with seas, joined previously isolated territories, and then divided them again. Each time, living organisms had to respond to new conditions. At the beginning of the Mesozoic, almost all land belonged to Pangaea. On a map, that looks convenient, one enormous continent across which animals could theoretically disperse over vast distances. But joining so much land together had serious climatic consequences. The ocean moderates temperature and supplies moisture. The farther a region lies from the coast, the weaker its influence becomes. The interior of Pangaea lay thousands of kilometers from the sea. Moist air masses could not always penetrate that far, and rainfall was distributed extremely unevenly. Large areas were arid, strongly seasonal, and subject to sharp temperature fluctuations. This is known as climatic continentality. The term is only complicated at first glance. Its meaning is simple. The ocean is far away, so summers become hotter, the cold season more pronounced, and rainfall less reliable. Yet it would also be wrong to turn all of Pangaea into one endless desert. The giant continent crossed many latitudes. Humid regions existed around its margins, and powerful monsoon systems operated in several areas. Seasonal winds brought torrential rain, followed once again by long dry periods. Relief intensified the contrasts. Mountain ranges blocked moist air, while a rain shadow formed behind them, a vast region that received very little precipitation. Even then, there was no single climate for the age of dinosaurs. At the same moment, Earth could contain dry interior plains, humid river valleys, seasonal forests, and cool regions at high latitudes. A global average temperature tells us little about a specific place unless we also consider latitude, elevation, proximity to the ocean, and the direction of air currents. For early dinosaurs, these differences imposed real limits. Some groups could survive intense seasonality, others depended on stable vegetation and permanent sources of water. Climatic zones acted as invisible barriers. The land may formally have remained connected, but not every population could cross the arid equatorial belt. Then Pangaea began to break apart, and the rules changed. The fracturing of the supercontinent was not a single event, but a prolonged process. Earth's crust stretched, deep fissures opened, enormous eruptions occurred, and separate areas of land slowly moved apart. New marine basins formed between them. At the beginning of the Jurassic, the Atlantic Ocean that now separates the Americas, Europe, and Africa was only an emerging system of rifts and narrow bodies of water. When an ocean appears between continents, far more changes than a line on the map. Marine currents are reorganized, and ocean currents are one of the planet's primary mechanisms for distributing heat. They carry warm water from low latitudes towards higher ones and influence coastal temperatures, atmospheric humidity, and the position of rainfall belts. New seas brought moisture to regions that had previously lain deep inside the continent. In some places, arid lands became wetter. Elsewhere, changing coastlines disrupted the former circulation of air and increased dryness instead. Bays, lowlands, marshy plains, and long river systems formed. A landscape could be transformed faster than its fauna could adapt. For dinosaurs, this meant a constant redistribution of suitable territory. The expansion of humid forests opened space for large herbivores, and predators followed them. Retreating forests reduced the food supply and divided populations. A change in the course of a major river could split one continuous group of animals into several isolated ones. Geography intervened directly in evolution. At first, the breakup of Pangaea did not merely divide worlds. It sometimes connected them as well. As long as land bridges remained between future continents, animals could move from one region to another. Then, a bridge sank beneath the water or was destroyed by tectonic processes, and the connection ended. Populations that had exchanged genes only recently began to develop independently. That is how geographic isolation works. If two groups of the same species are separated for long enough by a sea, a mountain system, or an unsuitable climatic zone, each adapts to its own conditions. One region may contain more food, while another has greater pressure from predators. Large size may be advantageous in one place, while limited resources favor smaller forms elsewhere. Differences accumulate, and eventually, one ancestral lineage gives rise to separate species. The Mesozoic offered enormous opportunities for this process. Laurasia and Gondwana continued to fragment. South America separated from Africa. India became an isolated landmass and moved north. Australia and Antarctica remained connected for a long time, although their positions gradually changed. Routes of dispersal between North America, Europe, and Asia appeared and then disappeared again. As a result, dinosaurs did not evolve as one uniform global fauna. The southern continents developed their own lineages of large predators and sauropods. Different communities formed in northern regions. Even neighboring territories could differ markedly if a sea, mountain region, or climatic barrier arose between them. This mechanism became particularly clear during the Cretaceous, when sea level stood substantially higher than it does today. At certain times, the difference may have exceeded 100 meters, although precise estimates depend on the method of reconstruction. The cause was not merely the absence of large, permanent ice sheets. During the Cretaceous, new oceanic crust was forming actively. Mid-ocean ridges, long submarine mountain systems where mantle material rises and creates new seafloor, occupied a greater volume than they do today. They displaced water towards the edges of the oceans. Warm water expanded further, while continental ice sheets did not lock away large quantities of water. As a result, the seas advanced across low-lying land. During the late Cretaceous, the western interior seaway cut across North America. It stretched for thousands of kilometers and connected northern waters with the region of the modern Gulf of Mexico. The continent was effectively divided into two parts, Laramidia in the west and Appalachia in the east. For terrestrial animals, this was more than a new coastline. It was a barrier that large dinosaurs could not cross freely. Populations on opposite sides of the sea evolved separately. The western coast changed as well. The sea repeatedly advanced and retreated, compressing the habitable land and then exposing vast plains once again. Rich communities of horned and duck-billed dinosaurs arose on the relatively narrow landmass of Laramidia. Some researchers suggest that even within this territory, there were distinct northern and southern faunas. The question remains debated. The fossil record is incomplete, and differences between finds may partly reflect the ages of the rocks and the uneven intensity of excavation. But the mechanism itself is not in doubt. The more fragmented an environment becomes, the more opportunities it creates for regional evolution. For much of the Cretaceous, Europe was not a continuous continent, but an archipelago. Areas of land were surrounded by shallow seas, isolating local populations. Islands impose distinctive evolutionary rules. When resources are scarce, large animals sometimes become smaller, producing island dwarfism. Small forms, by contrast, may grow larger if former predators and competitors disappear. That is why the European fossil record contains unusual island dinosaurs that differed noticeably from their relatives on large continents. Their size and anatomy were determined not by an abstract age of giants, but by the area of available land, the amount of food, and the degree of isolation. High sea levels affected even animals that never approached the coast. Advancing water reduced the area of land, divided river basins, and altered regional climates. Marine air masses penetrated farther into the continents, increasing humidity in some areas. Elsewhere, reorganized currents may have reduced rainfall. When the sea retreated, new plains emerged and were colonized by plants, herbivores, and the predators that followed them. Every such change produced winners and losers. Species with wide geographic ranges and flexible diets generally endured the reorganization more easily. Highly specialized animals that depended on particular vegetation or a particular type of landscape were more vulnerable. Sometimes they needed only to move with their familiar habitat. But if a sea or mountain chain blocked the route, there was nowhere left to retreat. Here we need to dismantle another common simplification, the idea of the Mesozoic as one continuous tropical greenhouse. On average, much of the Mesozoic really was warmer than the present. Temperatures were especially high during certain intervals of the Cretaceous. Permanent ice caps were either absent or considerably smaller than those of today, and forests grew far beyond the polar circles. But warmer than today does not mean tropical everywhere. At high latitudes, light still followed a pronounced seasonal cycle. Even with relatively mild temperatures, the polar night did not disappear. For months, plants lived in weak light, or almost none at all, shedding their leaves or slowing their growth. Animals had to endure long, dark seasons, search for food, migrate, or possess physiological adaptations to the cold. The Mesozoic also contained major climatic fluctuations. The Triassic included prolonged arid intervals, but it also experienced periods of sharply increased humidity. Jurassic climate changed as Pangaea broke apart and the oceans were reorganized. During the Cretaceous, there were episodes of extreme warming, disrupted ocean circulation, and changes in oxygen levels in the deep sea. Towards the end of the period, some regions showed a trend towards cooling and stronger seasonality. Scientists do not reconstruct these changes from one line of evidence. The chemistry of marine shells helps estimate the temperature of ancient water. Ratios of oxygen isotopes act as a climate indicator, although they require careful interpretation. Sedimentary rocks reveal where seas, deserts, rivers, and wetlands once lay. Coal points to the prolonged accumulation of plant matter in humid conditions. Evaporites, salts left behind when water evaporates, indicate arid environments. Fossil leaves, pollen, and wood help reconstruct vegetation and seasonality. No single indicator provides the entire picture. A paleoclimate reconstruction takes shape when different kinds of evidence begin to agree. Serious science therefore discusses not only its conclusions, but also the limits of their precision. The oxygen question is more complicated still. A popular explanation often comes down to one sentence: dinosaurs became enormous because there was supposedly far more oxygen in the Mesozoic. That statement is far too crude and, for some periods, simply wrong. Oxygen concentrations changed throughout the Mesozoic, and different models produced different values. During certain intervals, levels may have been higher than today. During others, lower or roughly similar. There is no reliable, direct scale covering the entire era. Moreover, the large size of dinosaurs cannot be explained by one atmospheric measurement. It depended on the respiratory system, skeletal structure, growth rate, reproduction, available food, and pressure from other animals. Gigantism was a biological response to particular conditions, not an automatic consequence of unusual air. The central conclusion is uncompromising. The strength of an individual animal can never explain the history of an entire group. A dinosaur might be enormous, fast, and well-armed, but if the sea destroyed its habitat, climate reduced its food supply, and its population became trapped on a small area of land, anatomical superiority ceased to be decisive. The reverse was also true. A small group entering a new region without its former competitors gained the opportunity to expand rapidly and produce several new forms. The planet continually redistributed opportunities of this kind. The breakup of Pangaea did more than create the modern continents. It multiplied the number of isolated evolutionary worlds. New oceans changed the transfer of heat. High seas fragmented the land. Mountain systems redirected air currents. Climate zones shifted, forests advanced and retreated, and entire animal communities moved with them. There was therefore no single formula for dinosaur success. What worked on a humid coastal plain might be useless in a dry continental interior. A species that flourished on a large continent might shrink or disappear on an island. A predator perfectly adapted to a particular prey became vulnerable when climate altered the vegetation and reduced the number of herbivores. Dinosaurs ruled the land for so long precisely because they were not one type of animal, but an immense collection of evolutionary solutions. Some lineages disappeared and others took their place. Continents separated, and once unified groups became regional. Seas retreated, and newly exposed territories were colonized again. The planet did not choose its winners in advance. It changed the conditions, sometimes gradually and sometimes catastrophically. The history of dinosaurs unfolded in a constant effort to keep pace with those changes. The planet could create an ecological opportunity, but only an animal whose body could withstand its own scale could exploit it. This brings us to one of the hardest questions in the entire history of dinosaurs. How did nature build a terrestrial vertebrate weighing tens of tons, an organism that walked, breathed, fed, and grew without collapsing beneath its own mass? Even the largest land mammals never reached the size of the most massive sauropods. A modern African elephant generally weighs several tons. The extinct Paraceratherium, a gigantic, hornless relative of the rhinoceros, may have weighed around 15, or, by some estimates, 20 tons. The mass of the largest prehistoric proboscideans remains disputed. Yet some sauropods, such as Argentinosaurus and Patagotitan, probably weighed between 50 and 70 tons, and some estimates rise even higher. Exact figures are impossible. Complete skeletons of the largest animals are almost never preserved, so mass has to be reconstructed from individual bones, the proportions of related species, and three-dimensional models. There is little value in holding a contest for the title of heaviest dinosaur on the basis of a difference of a few tons. What matters is the order of magnitude. Sauropods moved far beyond any limit ever reached by terrestrial mammals. Let us follow how this became possible, beginning with the earliest moment in the life of an imaginary sauropod. It does not appear as a miniature copy of a multi-ton adult, but as a relatively small hatchling emerging from an egg. Even the eggs of the largest sauropods were not monstrously large. Many known specimens are comparable in size to a large ball, and a hatchling may have weighed only a few kilograms. At first glance, this seems contradictory. An animal destined to outweigh several elephants begins life in an egg that is not especially astonishing. Yet this is where the first important advantage lies. A mammal develops inside its mother's body. The larger the offspring, the more resources pregnancy requires, the greater the strain on the body, and the longer the period of gestation. Birth is followed by prolonged nursing, and in many large species, years of care. This strategy produces well-developed offspring, but sharply restricts the rate of reproduction. Sauropods laid eggs. That does not mean reproduction was easy or safe. An egg had to be formed, laid, and placed under suitable conditions. The embryo needed particular levels of temperature and moisture. A large proportion of clutches probably failed, and many hatchlings became prey. But the female did not have to carry every offspring until it reached a mass of hundreds of kilograms. She could lay several eggs at once and later produce new clutches. The evolutionary strategy was not to invest vast resources and time in raising one almost finished giant, but to produce many small offspring, only some of which would reach maturity. That is a fundamental difference. The size of an adult sauropod was only weakly connected to the size of the newborn. In terrestrial mammals, that connection is much stronger. The egg itself imposed a physical limit. Oxygen had to enter through the shell, and carbon dioxide had to leave. If an egg became too large, gas exchange presented a problem. The volume of its contents increased faster than the surface area of the shell. Sauropods could not simply lay eggs the size of cars. The giant had to be built after hatching, and it was built quickly. Our imaginary hatchling leaves the nest small, vulnerable, and surrounded by animals capable of eating it. Its main task during the first years is to escape that dangerous weight class as quickly as possible. The larger it becomes, the fewer predators are able to attack it. Bone histology, the study of microscopic bone structure, reveals the growth rate of sauropods. A thin section of fossil bone can show the organization of the tissue, traces of blood vessels, and lines marking slower growth. It is not a perfect calendar, but it allows us to reconstruct the general pattern. The bones of young sauropods contain rapidly formed fibrolamellar tissue. It was richly supplied with blood and is characteristic of animals undergoing intense growth. A sauropod did not add a little mass at a time over several centuries. It gained most of its weight within a few decades, growing especially quickly while young. Rates differed among species, but the largest forms may have added hundreds of kilograms, and, during some intervals, possibly more than a ton per year. This is not the slow physiology of a familiar cold-blooded reptile. Judging by the rate at which their bone formed, sauropods had a fairly high metabolism. How closely it resembled that of modern birds or mammals remains a subject of research. Their physiology probably changed with age and size, but the image of a sluggish giant that grew almost imperceptibly and spent most of the day basking in the sun fits the evidence poorly. Rapid growth required a colossal quantity of food, and here the sauropods solved the problem in a completely different way from large herbivorous mammals. An elephant, rhinoceros, or cow processes food thoroughly with its teeth. Chewing breaks down plant tissue and aids digestion, but it comes at a cost. It requires large teeth, powerful jaw muscles, and a strong skull. The head becomes heavy. The head of a sauropod remained remarkably small in relation to its body. In many species, the teeth were concentrated towards the front of the jaws and served to grasp or strip vegetation. There was no complex chewing apparatus. The animal bit off branches, leaves, or shoots and swallowed them quickly, with very little processing in the mouth. This was not a primitive shortcoming, but a key solution within the entire design. Abandoning extensive chewing made the skull lighter. A small head could then be carried far from the body on a long neck. If a heavy skull with massive jaws had sat at the end of a neck several meters long, the strain on the vertebrae and muscles would have been immense. Every additional kilogram in the head would have produced considerable torque. In simple terms, it would have pulled the entire structure down like a heavy load at the end of a long lever. The sauropod avoided that problem. The head performed a relatively simple task: seize food quickly and pass it onwards. Most processing took place inside the massive digestive tract. The enormous torso provided space for a voluminous gut in which plant matter could ferment for a long time with the help of microorganisms. The longer the material remained inside, the more nutrients could be extracted even from low-quality food. Large size reinforced itself. A big body housed a large digestive system, and that system made it possible to sustain a big body. The importance of the long neck now becomes clear. It is often explained solely as a means of reaching treetops. That genuinely mattered for some sauropods, although neck posture differed among species and is not reconstructed in the same way for all of them. Some may regularly have fed high above the ground, while others held the neck more horizontally and gathered vegetation at medium or low levels. The primary advantage was a larger feeding envelope. Standing almost in one place, the animal could cover an immense area, sweeping its head sideways, lowering it to the ground, or raising it higher. The heavy torso and limbs moved less, while the light head collected food over a wide radius. For an animal weighing tens of tons, that represented a serious saving. Every step costs energy. If a broad strip of vegetation can be harvested without moving the whole body, daily expenditure falls. The neck functioned not merely as a crane, but as an efficient feeding tool. The neck itself, however, also had to remain reasonably light, despite its length. This is where another part of the system enters the picture: skeletal pneumaticity. Sauropod vertebrae contained cavities that were probably connected to air sacs in the respiratory system. A bone might appear massive from the outside, but internally it was not a solid, heavy block. A complex network of struts maintained strength while reducing mass. A similar principle is used in engineering. Material is placed where it bears the main load, while unnecessary volume is removed. In the sauropod, however, evolution created the design. Pneumaticity was especially pronounced in the neck and front trunk vertebrae. It did not make the entire animal almost weightless. That is a clear exaggeration. Most of the mass still lay in the muscles, internal organs, and limbs. But without lighter vertebrae, the long neck would have been considerably heavier and would have required even more powerful muscles. Muscles themselves have mass and need energy. Reducing the weight of one part of the structure lowered the strain on all the others. The traces of air-filled cavities suggest that sauropod respiration resembled the avian system. In birds, the lungs are relatively rigid, and air moves through them with the help of a system of air sacs. The flow is arranged so that gas exchange can occur very efficiently during both inhalation and exhalation. We cannot see the soft organs of a sauropod directly. They almost never fossilize. But the structure of the vertebrae, together with the relationship to birds and other dinosaurs, provides strong grounds for reconstructing a system of air sacs. For a gigantic organism, that may have offered several advantages at once. Gas exchange became more efficient, the front of the skeleton became lighter, and air moving through the body may have helped remove heat. That final task was critical. The larger an animal becomes, the smaller the surface area of its body in relation to its volume. Heat is produced throughout the mass of its tissues, but is lost mainly through the surface. A small animal heats and cools quickly. An enormous one loses heat slowly. This phenomenon is called thermal inertia, and in large animals it is sometimes described as gigantothermy. Large size helps maintain a relatively stable temperature, especially at night or when the weather changes. But in a hot climate, the same advantage becomes a threat. Once the body overheats, cooling tens of tons of living tissue quickly is extremely difficult. Sauropods had to regulate their activity, choose when to feed, use shade, and perhaps release some heat through the respiratory system. Body temperature may also have varied with age. Small juveniles exchanged heat rapidly with the environment, while adult giants became far more thermally inert. The skeleton not only had to remain light, it also had to bear the weight. Sauropod limbs stood vertically beneath the torso and functioned as strong supporting columns. This posture requires less continuous muscular effort than widely spread, bent legs. Joint surfaces were adapted to immense loads, while broad feet distributed pressure across the ground. That does not mean a sauropod could barely move. Trackways show a confident, coordinated gait. But its body was not designed for sudden leaps or rapid galloping. The greater the mass, the more dangerous a dynamic load becomes. During rapid acceleration, a turn or a fall, bones and joints experience forces far greater than the simple weight of a standing animal. For a giant, a fall could be catastrophic. An injured limb meant losing the ability to reach food and water. The entire structure was therefore designed not for acrobatics, but for stable, economical movement. As our imaginary sauropod grew, it gained more and more advantages. Fewer predators could attack it. The digestive system increased in volume. Body temperature became more stable. The long neck opened access to food beyond the reach of smaller animals, or allowed vegetation to be gathered over a broad area. But every advantage carried a cost. An adult sauropod required an enormous quantity of plant matter every day. If vegetation disappeared because of drought, fire, or climate change, a large body quickly became a problem. Traveling between feeding grounds required energy and water. A herd of giants could noticeably alter the surrounding landscape in a short time. Circulation posed a separate challenge. If the animal raised its head far above its heart, blood had to be driven up the long neck. That required high pressure and a powerful cardiovascular system. How often different sauropods held their heads vertically remains debated. For species with especially long necks, a continuously elevated posture may have been physiologically expensive, so actual movement probably depended on the anatomy of the particular animal and the conditions under which it fed. Reproduction remained a vulnerable stage as well. An adult giant was beyond the reach of most predators, but its eggs and offspring were not. The enormous difference in size between juveniles and adults meant that they effectively lived in different ecological worlds. Young animals ate differently, moved differently, and faced different predators. Only a small number survived until size became a defense. Sauropod gigantism, therefore, cannot be explained by a single cause. There was no special gene for immense size, no miraculous climate, and no kind of air that automatically transformed animals into giants. Highly productive vegetation may have helped, but food alone was not enough. We have already examined the claim that oxygen remained permanently elevated. It is not supported across the entire Mesozoic and does not explain sauropod anatomy. What worked was a system of interconnected traits. Eggs allowed life to begin at a small size and prevented adult mass from being tied to a prolonged pregnancy. Rapid growth helped juveniles leave the most dangerous stage sooner. Simple teeth and the absence of prolonged chewing kept the head light. A long neck expanded the feeding area without requiring the whole body to move constantly. A voluminous gut extracted energy from large quantities of coarse vegetation. Air-filled cavities lightened the spine. An efficient respiratory system supplied oxygen to active tissues and may have helped remove heat. Upright limbs carried the weight at a lower energetic cost. Remove one element from this design, and the others begin to work less effectively. Make the head heavy, and the long neck demands excessively powerful muscles. reduce the digestive system, and low-quality food no longer provides enough energy. Slow the rate of growth, and the young animal remains easy prey for too long. Replace eggs with a prolonged pregnancy carrying a large fetus, and the population's reproductive rate falls sharply. That is why the largest terrestrial mammals did not follow the sauropod path. It is not because mammals are built badly. Their reproductive strategy, chewing apparatus, metabolism, and body plan form a different set of compromises. In the water, mammals did surpass sauropods. A blue whale is heavier than any reliably estimated dinosaur, but water supports the body and removes much of the load from the limbs and spine. On land, every additional kilogram has to be held against gravity. Sauropods came closer to that limit than any other animals. They did so not through one miraculous adaptation, but through a rare convergence of many solutions, each supporting the rest. Our imaginary hatchling began life weighing only a few kilograms. Within several decades, it became an animal whose heart supplied blood to an immense body, whose legs carried tens of tons, and whose head could gather food many meters away. It was not simply an enlarged lizard. It was a fundamentally different biological design, one of the most radical experiments evolution has ever conducted on land. We have just followed the way a small sauropod hatchling could become a multi-ton giant. But a natural question follows. How do we know how quickly it grew, when it reached maturity, and what happened throughout its life? A paleontologist usually receives neither a living animal nor even a complete skeleton, but a few fossilized bones that have lain in rock for tens of millions of years. The answer requires discipline. Bones really can reveal an astonishing amount, but they do not tell the story on their own. They have to be compared with eggs, nests, tracks, the chemistry of rocks, skeletal injuries, and the anatomy of living animals. A reliable reconstruction emerges only when independent lines of evidence converge. Even then, it remains a reconstruction, not a recording of the past. Let us begin with growth. On the surface, a fossil bone looks like a motionless mineral object. Under a microscope, it becomes an archive of physiological processes. Paleontologists study it through paleohistology, examining thin sections of bone tissue and reconstructing the way the bone formed during the animal's life. In rapidly growing bone, fibers and blood vessels are organized differently from those in tissue deposited slowly. Fibrolamellar bone is found in many dinosaurs. This tissue contains a dense network of vascular channels and is characteristic of intense growth. It shows that the organism did not merely increase slowly year by year, like many modern reptiles. It was actively building mass. Bones also contain lines marking pauses or slowdowns in growth. These formed during periods when the production of new tissue temporarily declined, perhaps because of seasonal food shortages, drought, or other physiological stress. They are often compared with the annual rings of a tree, but that comparison must be used carefully. Not every line necessarily represents exactly one calendar year, and the inner regions of an adult bone may be remodeled, erasing the early record. Bone is a living organ. As long as the animal is alive, old tissue is partly broken down and replaced by new tissue. This process is called remodeling. In a large adult dinosaur, it could destroy the record of the earliest years, so age cannot be determined simply by counting every visible ring. Researchers compare different bones, study young and adult members of the same species, measure the spacing between growth lines, and construct approximate curves of changing body mass. That is how we discovered that many dinosaurs grew substantially faster than most living reptiles. Small species could approach adult size within a few years. Large predators and herbivores required decades, but their most intense growth occurred while they were young. Tyrannosaurus, for example, underwent a period of rapid weight gain during adolescence. A young animal was not merely a reduced version of the adult. It had a lighter body, long legs, and probably hunted differently. As it grew, the skull became more massive, the jaws more powerful, and the entire way of life may have changed. An important picture emerges. During its lifetime, a dinosaur could occupy several ecological roles. A hatchling, an adolescent, and a giant adult may have eaten different prey, chosen different territories, and faced different threats. A single biological species effectively spread its pressure across several levels of the ecosystem. How precise are such conclusions? The general sequence of growth can be reconstructed with reasonable confidence. Specific values, such as exact mass at a particular age, depend on a model. To calculate them, researchers must first estimate body volume from the skeleton, then assume a density for the tissues, and only then connect bone size with age. Error at every stage affects the result. Serious research, therefore, usually reports a range rather than one magical number. When a popular account states that a particular dinosaur gained an exact number of kilograms per year, far more uncertainty often lies behind that precision than it appears. The next part of life begins before the hatchling emerges. Eggs and nests are preserved less often than bones, but they provide some of the most direct evidence of reproduction. The shape of an egg, the thickness of its shell, and its microstructure reveal how gas exchange occurred. The shell contains microscopic pores through which the embryo received oxygen and released carbon dioxide. Their number and arrangement help determine whether the egg lay exposed to the air, was covered with plant matter, or was partly buried in the ground. If embryonic bones are preserved inside, there is a chance of identifying which animal laid the egg. That is crucial because eggs that look similar may belong to different groups, while the same dinosaurs may lay eggs under different conditions. Without an embryo, the connection between an egg and an adult species often remains tentative. Entire nesting grounds reveal not a single event, but repeated behavior. In some places, dozens of nests have been found within a limited area, allowing us to speak of nesting colonies. The animals probably returned to suitable regions and laid their eggs near one another, but the word colony does not yet imply a complex society. Dozens of modern sea turtles lay eggs on the same beach without forming family groups or raising their young together. A concentration of nests may indicate a shortage of suitable sites, seasonal migration, or the safety of a location rather than sophisticated social organization. One of the best-known examples is Maiasaura. Its name means caring mother lizard. The remains of young animals were found near nests. They had already grown considerably, but were still within the nesting area. At first, this was treated as compelling evidence that adults brought them food. Today, the interpretation is more cautious. The young animals may indeed have remained at the nest for some time, and care by adults is entirely plausible. The bones themselves, however, do not show the moment of feeding. We cannot see who brought food, how long the young depended on their parents, or whether each nest was guarded by a particular individual. More direct evidence of behavior comes from the skeletons of some oviraptorosaurs and bird-like dinosaurs preserved directly on top of their clutches. The adult lay over the eggs, with its forelimbs arranged around them. The posture closely resembles brooding in modern birds. The connection between the body and the clutch is strong in this case. The animal clearly did not end up on top of the eggs by accident. But even this evidence has limits. We can say that the adult dinosaur covered or warmed the clutch. We cannot automatically conclude that it then fed the hatchlings for months or formed a stable pair bond. The paleontology of behavior almost always works this way. One trace confirms a particular action, but it does not give us permission to invent an entire way of life. Sometimes evidence of reproduction lies inside the bone itself. Tissue resembling the medullary bone of modern birds has been found in certain dinosaurs. Female birds temporarily form this tissue before laying eggs, using it as a store of calcium for the shell. If such tissue is correctly identified in a fossil animal, we are looking not merely at a female, but at an individual that was reproductively active shortly before death. Similar structures have been described in Tyrannosaurus, among other dinosaurs. Diagnosis requires caution, however, because a pathological bone change can sometimes resemble reproductive tissue. Researchers compare the microstructure, chemical composition, and location of the area. One unusual thickening is not enough. Nests preserve one episode, while trackways preserve a few seconds or minutes of movement. Yet they allow us to see what a skeleton cannot reveal. Footprints show how an animal placed its foot, how long its stride was, and in which direction it moved. The distance between prints and the approximate height of the limb can be used to estimate speed. A sequence of tracks sometimes records acceleration, a turn, or a stop. Several parallel trackways may indicate a group traveling together, and once again, only may. If the tracks of different animals point in one direction and cross the same layer of rock, that is a strong argument that they moved at the same time. But when the temporal resolution is poorer, individual animals may have followed the same route hours or days apart. A riverbank, narrow passage, or water's edge naturally directs everyone along the same line, even when they do not form a herd. Beautiful hunting scenes require particular caution. A predator's footprint beside the tracks of a herbivore does not yet prove a chase. The animals may have passed through at different times. Genuine cases in which direction, distance, and deformation of the ground allow us to discuss an interaction are rare. That is precisely why they are so valuable. Bones preserve longer events, injuries, and disease. A healed fracture means that the animal survived the injury and lived long enough for recovery to begin. The shape of the callus shows how the body stabilized the damaged area. A deformed joint may indicate arthritis. Irregular, eroded surfaces sometimes point to infection. Tooth marks record an attack, a fight, scavenging, or even conflict between members of the same species. If a bite had time to heal, it was inflicted while the animal was alive. If the margins show no tissue response, the mark may have appeared after death when scavengers fed on the carcass. This is an important distinction. Living bone responds to trauma. Dead bone does not. A healed fracture, however, does not prove that the injured dinosaur was treated or fed by members of its group. It may have survived alone, especially if the injury did not completely prevent movement. Social assistance is possible, but the callus itself does not confirm it. Here, it is especially easy to replace evidence with an emotionally appealing story. One of the strongest examples of paleopathology involves a young, long-necked diplodocid nicknamed Dolly. Researchers discovered unusual bony growths on several cervical vertebrae. They occurred in areas that, during life, were penetrated by extensions of the respiratory air sacs. Computed tomography and examination of the surface showed that this was not ordinary deformation after death. The bone had time to react to a pathological process. The most likely explanation was an infection of the respiratory system that spread into tissues associated with the air sacs. In modern birds, similar lesions may occur with air saculitis, and inflammation of the air sacs. It can be caused by bacteria or fungi, including pathogens capable of producing severe respiratory failure. If the analogy is correct, the sauropod may have suffered from difficulty breathing, weakness, loss of appetite, and fever. This is a rare moment when a fossil brings us close not merely to a cause of death, but to the physical experience of the animal. We are no longer looking at an abstract skeleton, but at a young organism for which breathing may have become increasingly difficult. An exact diagnosis is impossible. We have no blood test, sample of soft tissue, or culture of the microorganism. Tens of millions of years later, the reaction of the bone survives, not the entire clinical process. We can reasonably speak of a disease probably associated with the air sacs. Naming a particular pathogen and exact cause of death would go beyond the evidence. This case clearly demonstrates both the power and the limits of the method. Pathology leaves a recognizable trace. Comparative anatomy connects the affected region with the respiratory system. Observations of modern birds suggest a probable mechanism, but every additional level of detail becomes less certain. Almost everything we know about the everyday lives of dinosaurs is built this way. Bone microstructure reveals growth rate, but exact age depends on preservation and the model used. Nests confirm reproduction at a particular site, but do not reveal the entire family organization. A skeleton on a clutch demonstrates brooding, but does not tell us how long parents cared for their young. Parallel tracks permit an interpretation of group movement, but do not always prove the existence of a herd. A healed fracture shows survival after injury, but not necessarily assistance from companions. The more independent signs agree, the more confident the conclusion becomes. If one location contains nests, animals of different ages, repeated nesting layers and tracks left by adults, the case for persistent nesting behavior becomes stronger. If a conclusion rests on one deformed bone, the range of possible explanations remains broad. This is not a weakness of paleontology. On the contrary, the ability to separate what is established from what is probable, or merely possible, is a mark of mature science. Weakness begins when probability is presented as fact, and empty spaces are filled with a convenient story. Even so, the combined traces bring dinosaurs much closer than we might expect. They hatched from eggs, survived a dangerous youth, grew rapidly, broke bones, suffered bites, endured infections, and sometimes lived for years with the effects of old injuries. Some guarded their clutches, others gathered at shared nesting grounds. Some traveled in groups, although the stability and organization of those groups may have differed completely. These are not motionless museum constructions or a collection of perfect fighting machines. They are living organisms with complex physiology, a limited lifespan, and bodies that could fail. Their daily lives vanished, but not without a trace. They remain in the microscopic structure of bone, the shell of a crushed egg, a sequence of footprints, and a fracture that once had time to heal. The researcher's task is not to force these traces to say more than they can, but neither should we underestimate what they have already told us. After bone sections, nests, tracks, and pathologies, we can see especially clearly how carefully science reconstructs an extinct animal. Cinema works differently. It needs a recognizable image, comprehensible action, and powerful emotion. The dinosaur on screen is therefore not always a reconstruction. Often, it is a fictional character assembled from scientific evidence, outdated ideas, and the demands of spectacle. The first illusion concerns behavior. In films, a dinosaur is usually pursuing prey, fighting, or preparing to attack. When a large predator enters the frame, it is almost required to notice someone immediately and begin a chase. In a real ecosystem, that behavior would be too costly. Active hunting requires energy and carries a risk of injury. For a multi-ton predator, a bad fall or damaged limb could be fatal. Most of the time, therefore, it was not attacking. It was resting, searching for signs of prey, drinking, digesting food, avoiding overheating, and choosing a moment when the cost of an attack was justified. The same applies to herbivores. Their lives did not consist of endless flight. They fed, moved between patches of vegetation, reproduced, guarded space, and responded to danger only when a threat truly appeared. Cinema compresses months of ordinary life into a few minutes of rare events. That is effective drama, but a poor model of behavior. The second error is the impression that almost all dinosaurs were giants. Large bones are easier to notice in a museum, and an enormous animal is easier to sell to an audience. On screen, the Mesozoic therefore often becomes a world in which every creature is larger than a human. In reality, dinosaurs included many small forms. Some were the size of a turkey, chicken, or pigeon. Even the famous velociraptor was considerably smaller than its familiar cinematic image. An adult measured roughly 2 meters from snout to tail, but probably weighed only around 15 or 20 kilograms. Small size did not make such dinosaurs unsuccessful or primitive. A small body needs less food, reproduces more quickly, and can occupy niches unavailable to giants. Small dinosaurs were as essential to Mesozoic ecosystems as small birds and mammals are today. Their delicate bones simply fossilized less readily, and long remained overshadowed by more spectacular discoveries. The third image science has changed particularly dramatically is the skin of predatory dinosaurs. For most of the 20th century, theropods were depicted as almost entirely scaly. Then, numerous specimens appeared bearing impressions of feathers and filament-like coverings. We now know that feathers did not belong only to the first birds. Many non-avian theropods had them, including several close relatives of Velociraptor. Some species retained simple down-like coverings. Others developed complex feathers on their limbs and tails. These structures could retain heat, serve in display, help cover a clutch, and, in certain lineages, later become part of the machinery of flight. But we should not replace one old simplification with a new one. Not every theropod was necessarily covered from head to toe in dense plumage. Patches of scaly skin are known in some large species. Coverings may have changed with age and differed between parts of the body. In adult Tyrannosaurus, for example, we have impressions of scales, but we do not know the complete body covering. Equally confident images of a wholly scaly and a completely fluffy Tyrannosaurus therefore go beyond the direct evidence. Finally, cinema creates sounds and colors, although evidence is especially scarce in both areas. A dinosaur's roar is generally assembled from modified calls of modern animals. It has to sound powerful, recognizable, and threatening. But the soft structures of the vocal apparatus almost never fossilize, so the voices of most species are unknown. Some dinosaurs may have produced low-frequency, closed-mouth calls resembling the booming sounds of certain birds or crocodilians. Others probably hissed, clicked, trumpeted, or used resonating structures. A full lion-like roar is an artistic option, not an established fact. Sometimes anatomy narrows the possibilities. The hollow crests of Parasaurolophus may have functioned as resonators, and computer models help estimate the possible pitch of their calls. Rare remains of laryngeal elements add further information. Yet, reconstructing the exact voice of an individual species is still impossible. Color presents a similar problem. For a long time, an artist could choose it almost freely. Today, researchers study melanosomes, microscopic structures associated with pigments, in some exceptionally preserved feathered dinosaurs. Their shape and distribution suggest dark, reddish, white, or iridescent areas of plumage. This has allowed bands, contrasting wings and parts of the pattern to be reconstructed in a few species. Such exceptional specimens are rare. The color of most dinosaurs remains unknown. Brown skin in older reconstructions was not scientifically proven, but a bright modern color scheme does not become fact merely because it looks bolder. An old film does not therefore always contain bad science. Sometimes it faithfully preserves the scientific image of the period in which it was made. At one time, an active dinosaur with a horizontally held body represented an important advance over earlier reconstructions of sluggish monsters dragging their tails. Then new discoveries appeared, and the image changed again. Science has no obligation to defend a familiar picture. If feathers, bone microstructure, or a new impression contradict an earlier reconstruction, the reconstruction has to change. Cinema can preserve one dinosaur forever. The scientific dinosaur will inevitably change with the evidence. Cinema has taught us to view the Mesozoic from the eye level of a large predator. The frame almost always contains something that can chase, bite, or defend itself. But lower your gaze to leaf litter, roots, small insects, and water, and the real work of the ecosystem comes into view. Dinosaurs were its most conspicuous participants, but they were not its foundation. The system began neither with a dinosaur egg nor with the first bite of a predator. It began with sunlight. Through photosynthesis, plants captured energy from the sun and converted carbon dioxide and water into organic matter. Only then did that energy become available to animals. The trunk of a giant sauropod, the muscles of a tyrannosaurus, and the horns of a ceratopsian were all ultimately built from energy once captured by a plant. It sounds obvious, but it leads to an unforgiving ecological rule. At every higher level of a food chain, a substantial share of energy is lost. It is spent on movement, breathing, temperature regulation, and the work of internal organs. Only a small fraction of the energy originally accumulated by plants reaches a large predator. A multi-ton theropod could therefore exist only where an immense mass of vegetation supported numerous herbivores. The pyramid worked from the bottom upwards, never the reverse. The Mesozoic plant world changed continually. Conifers, cycads, ginkgos, ferns, horsetails, and extinct seed plants played major roles during the Triassic and Jurassic. They formed forests, open woodlands, riverside thickets, and open expanses dominated by ferns. There was no single green wall surrounding the dinosaurs. Some plants tolerated drought, while others depended on humid lowlands. After fires, floods, and volcanic events, plant communities could be reorganized, and the distribution of animals changed with them. Different herbivores needed different food. Sauropods gathered large quantities of vegetation rapidly and processed it within capacious digestive tracts. Later, duck-billed dinosaurs possessed complex dental batteries, rows of continually replaced teeth forming powerful surfaces for grinding food. In ceratopsians, the beak cut vegetation while the rear teeth crushed and sliced it. This divided the resources. Some animals fed high above the ground, others grazed close to it. Some selected soft shoots, while others handled tougher plant material. This division is called ecological niche partitioning. It allowed several large species to live beside one another without competing directly for every leaf. But how do we know what they ate? Teeth reveal the mechanical work a jaw could perform. Scratches on enamel help show the direction of movement during a bite. The isotopic composition of tissues provides information about the water and vegetation in the diet. Occasionally, remnants of a final meal survive inside the torso, although such finds are rare and demand particular caution. Plant material may have entered the skeleton after death. One of the most convincing cases is the stomach contents of the armored dinosaur Borealopelta. They were preserved so well that researchers could distinguish fragments of plants. Ferns dominated the diet, and the animal appears to have selected particular parts of the available vegetation rather than indiscriminately swallowing everything green around it. Coprolites, fossilized feces, are no less important. They may not look impressive, but to a paleoecologist, they can be more valuable than a beautiful skull. They can contain ground plant tissue, wood, fungal spores, bone fragments, and other traces of food. If suitable animals are found nearby, and the size, shape, and contents match the expected diet, researchers can cautiously associate a coprolite with a particular group. Large coprolites from predatory dinosaurs contain crushed bone. This shows that powerful jaws did not always separate neatly. Parts of the prey's skeleton entered the digestive system as well. Herbivore coprolites contain not only leaves and twigs, but sometimes wood and fungal remains. Diets were more complex than the simple formula, a herbivore eats grass. Indeed, familiar grassy plains are misleading in this context. Grasses appeared during the Cretaceous, and their microscopic remains have even been found in some dinosaur coprolites. But extensive modern grasslands arose much later. Most large Mesozoic herbivores fed in communities with no exact modern equivalent. During the middle of the Cretaceous, the plant world underwent a major transformation. Flowering plants, or angiosperms, spread rapidly. Terrestrial ecosystems had already been complex and productive before their appearance, so it would be far too crude to say that flowering plants suddenly created modern nature. But they did change the relationships between plants and animals. Many angiosperms grew quickly, colonized disturbed ground, and used new reproductive strategies. The flower allowed pollen to be transferred with greater precision, while the fruit protected and dispersed seeds. Insects changed alongside the plants, feeding on their tissues, carrying pollen, or exploiting seeds and fruit. This relationship did not emerge in an instant. Insects had interacted with plants long before flowers appeared. Beetles, flies, and other groups may have carried the pollen of ancient seed plants. Fossil leaves preserve bite marks, larval tunnels, galls, tissue growths induced by insects, and damage left by sucking mouthparts. Flowering plants expanded the range of these interactions. Some insects became specialized for particular kinds of pollen or plant tissue. In turn, plants received more effective pollination. Coevolution emerged, a process in which changes in one group create selective pressure on another, whose response then feeds back in return. Amber preserves the finest individual snapshots of this world. Resin flowed down a trunk, trapping small arthropods, pollen, pieces of plants, and sometimes fragments of feathers. It then hardened into a transparent time capsule. Amber contains beetles, flies, wasps, ants, mites, and many tiny organisms that almost never survive through ordinary fossilization. Some specimens show parasites beside feathers. Others preserve insects with pollen on their bodies. This does not prove every specific ecological relationship, but it allows us to see participants in the system almost exactly where they were in life. Without insects, a Mesozoic forest would have functioned differently. They pollinated plants, ate leaves and wood, processed dead organic matter, and became food for small vertebrates. Their larvae lived in water, soil, and decaying vegetation. One small beetle may not have influenced the fate of a giant dinosaur directly, but millions of such organisms sustained the cycling of matter on which the productivity of the whole environment depended. Small vertebrates occupied the next level. Lizards, early mammals, amphibians, and small relatives of crocodiles lived between the dinosaurs' feet. They ate insects, seeds, fruit, eggs, and one another. They, in turn, became prey for young dinosaurs and small theropods. The image of the Mesozoic mammal as a tiny, helpless creature that did nothing but hide at night is also too simple. Most were indeed small, but they followed diverse ways of life. Some dug burrows, others climbed trees, and still others could swim. There were forms capable of attacking small dinosaurs. The remains of a young Psittacosaurus were discovered inside one fossil Rapenna. It is rare but direct evidence that relationships between dinosaurs and mammals did not always follow the pattern of a giant hunting a feeble little animal. A distinct system unfolded in freshwater habitats. Rivers, lakes, and marshy floodplains were not merely places where animals came to drink. The water contained its own food web, beginning with algae, microorganisms, and plant material. Small invertebrates fed on them, followed by fish and amphibians. Above them were large fish, crocodiliforms, and dinosaurs associated with aquatic prey. Terrestrial and aquatic systems exchanged matter constantly. Fallen leaves entered rivers. Fish became prey for land predators. Floods carried carcasses and organic material over long distances. Insects emerging from the water fed animals along the banks. The disappearance or deterioration of an ancient body of water therefore affected more than its immediate inhabitants. Even death did not remove an organism from the ecosystem. When a large dinosaur fell, its body became an immense reserve of matter and energy. Large predators and scavengers may have reached the carcass first. Tooth marks on bones show that flesh was stripped away, and sometimes the bones themselves were gnawed. Smaller animals and insects followed. Bacteria and fungi processed what remained. Organisms that break down dead matter are called decomposers. They reduce complex compounds to simpler ones and return chemical elements to soil and water. Without this process, nutrients would remain locked inside dead bodies, wood, and fallen leaves. plants would quickly exhaust the available supply of nitrogen, phosphorus, and other elements. Soil itself was one of the principal, yet almost invisible participants in the Mesozoic world. Microorganisms, fungi, and small invertebrates lived within it. Plant roots interacted with fungal networks to obtain water and minerals. Bacteria participated in the nitrogen cycle. Animals mixed the ground, made tunnels, and changed the access of air. This hidden labor determined how quickly vegetation recovered after a fire or flood, how many leaves grew during a new season, and how many herbivores the land could support. The number of herbivores, in turn, determined how many large predators the ecosystem could sustain. The result was a closed yet constantly changing system. Solar energy entered plant tissue. Herbivores converted it into movement and growth. Predators obtained only part of the stored energy by eating prey. Scavengers used the remains. Fungi, bacteria, and invertebrates completed decomposition and returned matter to the soil. Plants used it to build new leaves and trunks, and the cycle began again. In practice, the food web was more complex than one straight chain. An animal could be a predator, scavenger, and prey at the same time. Diet changed with age and season. Drought reduced vegetation, then lowered the number of herbivores, while the effects on large predators appeared later. A rich crop of seeds increased small animal populations and indirectly supported the animals that hunted them. That is why we cannot take one change, the spread of flowering plants, for example, and declare it the sole cause of a new surge in dinosaur diversity. In some groups, new plant resources may indeed have promoted specialization. But dinosaur evolution also depended on climate, geographic isolation, sea level, competition, and the legacy of existing lineages. The appearance of new plants and the flourishing of particular dinosaur groups do not always coincide closely enough to support a simple causal relationship. An ecosystem does not operate through one overriding cause. Large dinosaurs were the spectacular result of many processes taking place far away from them. A sauropod could consume vast quantities of vegetation only because soil returned nutrients, fungi and bacteria decomposed organic matter, insects participated in plant communities, and water carried mineral compounds across the landscape. A predator could grow to several tons only where the entire system produced enough herbivorous prey. The true rulers of the Mesozoic were therefore neither Tyrannosaurus nor sauropods, nor any other single group. They occupied the upper floors. The building rested on organisms that almost never received the leading role: plants, fungi, bacteria, insects, small vertebrates, and the inhabitants of bodies of water. This leads to an important systemic conclusion. The larger an animal is, and the higher it stands in the food web, the more strongly it depends on everything happening below. A giant may survive an attack, defend itself against a rival, and travel tens of kilometers in search of food. But if the foundation of the ecosystem collapses, size ceases to be an advantage. It becomes an expense the world can no longer afford. We have reached the moment when all the preceding threads converge on one question. Why did one global catastrophe help dinosaurs take possession of the world, while another destroyed every non-avian member of the group? The two events appear similar from a distance: abrupt climatic change, collapsing ecosystems, and the disappearance of many species. Yet their outcomes were opposite. The answer cannot be reduced to the magnitude of the blow. A mass extinction is not simply a very large catastrophe. What matters is how quickly it unfolds, which links in the food web it strikes first, how long the crisis lasts, and what options organisms possess when it begins. At the Triassic-Jurassic boundary, dinosaurs were not yet the undisputed rulers of the land. They shared ecosystems with numerous members of the crocodilian branch of the archosaurs, large amphibians, and other competitors. Then, around 201 million years ago, a series of powerful eruptions began in connection with the breakup of Pangaea and the formation of the Central Atlantic magmatic province. The volcanism released carbon dioxide and sulfur compounds into the atmosphere. Climate fluctuated sharply, the oceans became more acidic, and the carbon cycle was disrupted. Many groups that had previously occupied important terrestrial niches disappeared or declined severely. Dinosaurs survived the crisis comparatively well, although the reasons for their resilience are not fully established. A combination of traits probably helped: efficient respiration, the capacity for active movement, relatively rapid growth, insulating coverings in some lineages, and the ability to live in different climatic zones. But the most important consequence came after the catastrophe. Ecological niches opened, competition declined, dinosaurs gained room for adaptive radiation, a rapid divergence into many new forms. The first extinction did not create the dinosaurs or hand them a ready-made dominion. It changed the balance of power in their favor. What followed was a history lasting more than 130 million years. Continents split, new oceans formed, and plant communities changed. Dinosaurs survived climatic fluctuations, shifts in sea level and regional crises. Some lineages disappeared and others replaced them. Giant sauropods, armored herbivores, horned forms, duck-billed dinosaurs, and highly specialized predators emerged. Such prolonged success is easy to mistake for invulnerability, but evolution contains no trait that protects against every future threat. Every advantage works only under particular conditions. At the end of the Cretaceous, dinosaurs remained a diverse and widely distributed group. In some regions, the composition of the fauna may have been changing, and certain lineages declined before the final catastrophe. The fossil record for the closing part of the Cretaceous is uneven, so debate continues over whether dinosaurs were undergoing an overall decline. But there is no support for the claim that they had almost vanished by the time of the impact. The very latest Cretaceous rocks still preserve complex communities of large herbivores and predators. It was a living world. But it depended on a continuous flow of energy. Plants had to receive light and produce new organic matter. Herbivores needed fresh vegetation. Predators depended on herbivores. Enormous bodies that were effective in a stable, productive environment required a constant supply of food. Even if an adult giant could survive a brief drought, an entire population could not persist for long without its food base recovering. Around 66 million years ago, an asteroid roughly 10 or 12 kilometers in diameter struck the region of the modern Yucatan Peninsula. It was moving so fast that in seconds it released energy beyond comparison with ordinary geological events. The impact created the Chicxulub crater, around 180 kilometers wide. Close to the impact site, almost everything was destroyed by the shock wave, extreme heat, and ejected material. Enormous tsunamis swept through the surrounding seas. Earthquakes affected vast regions. Yet local destruction, however horrific, cannot by itself explain a global extinction. Most dinosaurs lived far from Yucatan. The decisive processes began after the impact. The asteroid struck rocks rich in carbonates and sulfates. Immense quantities of dust, soot, and sulfur-bearing aerosols rose into the atmosphere. Fine particles spread around the planet and sharply reduced the amount of sunlight reaching the surface. The so-called impact winter began. This does not mean that the entire Earth instantly acquired a permanent covering of snow. It refers to abrupt global darkness and cooling, whose exact intensity and duration are modeled across a range. But the basic physics is secure. Less sunlight means weaker photosynthesis, which means less new organic energy entering food webs. This was where the catastrophe struck the foundation of the system. Plants did not all vanish at once, but their productivity fell sharply. Leaves and shoots died because of cold, darkness, fires, and acid precipitation. In the seas, reduced light struck photosynthetic plankton, on which numerous marine organisms depended. A herbivorous dinosaur may have survived the moment the asteroid fell. It may have stood on the other side of the planet and suffered neither burns nor injury. But after a while, it faced a more dangerous problem. Its food was no longer being renewed. At first, the remaining leaves, branches, and roots were consumed. Then the reserves ran out. Large herbivores needed immense amounts of food and had to travel ever farther. Weakened animals endured cold and disease less effectively, escaped danger more slowly, and reproduced less often. The crisis then reached the predators. Their food supply declined with a delay, but inevitably. During the first days and weeks, carrion may have been abundant. Carrion, however, is a temporary resource. When herbivores cease reproducing, a large predator eventually has nothing left to pursue. This is a trophic cascade, destruction transmitted from one level of a food web to the next. The crisis begins among producers, then strikes herbivores, and only afterwards reaches the top predators. The higher an animal stands in the web and the more energy it needs, the less time it has. Gigantic size, which had provided protection for tens of millions of years, became a burden. A large animal requires more food. It reaches sexual maturity more slowly, and its population takes longer to recover. A broad feeding range becomes a problem when suitable territory disappears. Complex specialization stops working when the resource for which it was adapted vanishes. But size does not explain everything. Small, non-avian dinosaurs existed, and they disappeared too. Some birds became extinct, despite their small bodies and ability to fly. Pterosaurs vanished completely, and many were not giants. Small size alone was clearly insufficient. Survival depended on a combination of characteristics. The advantage belonged to organisms able to go without food for long periods, exploit varied resources, and use seeds, roots, carrion, and organic remains. Low energy requirements, a rapid reproductive cycle, the ability to shelter underground or in water, and the capacity to wait through the harshest interval all mattered. Food webs based on detritus, dead organic matter, proved more resilient than webs entirely dependent on fresh green biomass. Even when photosynthesis falls sharply, soil, bottom sediments, and forest litter still contain seeds, roots, wood, dead organisms, and other material. For a time, it can sustain bacteria, fungi, and small invertebrates, followed by the animals that feed on them. This helps explain the comparative resilience of some freshwater ecosystems. Rivers and lakes received organic matter from the surrounding landscape. Turtles and crocodilians had relatively slow metabolisms, could go without food for extended periods, and used aquatic refuges. Many mammals that survived the crisis were small, ate varied diets, and could shelter in burrows. Even here, however, there is no universal list of life-saving traits. Not every aquatic animal survived. Not every small creature crossed the boundary. Not every omnivore happened to be in the right place. The catastrophe was global, but its consequences varied by region, season, and environment. Sometimes geographic chance may have determined the fate of a population. The presence of a refuge, a store of seeds, proximity to fresh water, or the timing of the reproductive cycle. That is why mass extinction is both predictable and random. Predictable because certain characteristics improve the odds. Random because no characteristic guarantees the survival of a particular lineage. How do we know that an impact caused the final crisis? A thin layer corresponding to the boundary between the Cretaceous and Paleogene has been found in rocks around the world. It contains a sharply elevated concentration of iridium, an element rare in Earth's crust but more common in asteroids. The layer occurs in both marine and continental deposits, separated by great distances. The same boundary contains microscopic spheres of solidified melt and shocked quartz. This type of quartz forms under pressures that ordinary volcanism cannot produce. The age of the Chicxulub crater matches the timing of the mass extinction. Near the Gulf of Mexico, thick deposits associated with tsunamis and material ejected by the impact have been preserved. Each line of evidence on its own would leave questions. Together, they form a coherent picture. A major impact occurred, its products spread around the globe, and ecosystems changed abruptly in its aftermath. The asteroid did not strike a quiet planet. Massive eruptions of the Deccan Traps were already occurring in India. Immense volumes of lava erupted over an extended period, while volcanic gases affected climate and the chemistry of the oceans. Carbon dioxide may have produced long-term warming, while sulfur-bearing aerosols caused shorter episodes of cooling. The eruptions placed additional pressure on ecosystems before the impact and may have influenced recovery afterwards. The precise timing of individual volcanic phases and their contribution to the extinction remain under discussion. But setting up asteroid or volcanoes as a choice creates a false controversy. Deccan volcanism was an important background condition and possibly an additional stress factor. Yet the direct connection between the Chicxulub impact and the global extinction boundary is supported by several independent kinds of evidence. The asteroid need not be made the sole cause of every late Cretaceous change for us to recognize it as the principal trigger of the catastrophe. The most remarkable part of the story is that dinosaurs did not vanish completely. One branch made it through the crisis, the birds. Losses among birds were immense as well. Entire lineages disappeared, including many forms that had flourished during the Cretaceous. Flight alone offered no salvation. As forests collapsed, birds closely tied to trees and particular kinds of food lost their habitats just as terrestrial animals did. The ancestors of the surviving lineages were probably small and reasonably flexible in their diets. Some may have used seeds, a resource capable of remaining in the soil after green vegetation died. A toothless beak could handle different kinds of food, although it cannot be treated as the sole secret of survival. A ground-based way of life, a rapid reproductive cycle, mobility, and the ability to exploit temporary resources also mattered. After the catastrophe, fossil pollen records show what is known as a fern spike. Ferns colonize disturbed ground quickly because they spread by spores and make effective use of open soil. Their sudden increase reveals the scale of the destruction suffered by earlier plant communities. Forests did not return immediately. Recovery unfolded in stages. The surviving birds entered a world from which the former large competitors had disappeared. Their descendants later began to occupy the empty niches and produced the vast diversity we know today. There is a direct parallel with the beginning of the Jurassic. Catastrophe once again destroyed an old system and opened opportunities for the organisms that crossed the boundary. This time, however, most dinosaurs were not among the future winners, but among the lost upper levels of the ecosystem. That is how two catastrophes produced opposite results. At the Triassic-Jurassic boundary, a relatively young group survived the crisis, lost many competitors, and gained access to empty niches. At the end of the Cretaceous, the same broad evolutionary lineage already occupied many large and specialized positions. When the impact disrupted photosynthesis and cut off the flow of energy, the old advantages stopped working. Egg-laying allowed sauropods to produce many offspring, but it could not create food for them. Rapid growth helped the young leave a vulnerable age behind, but it required energy. An enormous body offered protection from predators, but became a liability during famine. Specialized teeth processed particular vegetation efficiently only while that vegetation existed. A catastrophe does not have to defeat an animal directly. It need only destroy the conditions under which that animal's body made sense. That is why the survivors are not necessarily the strongest, the largest, or the most complex organisms. They are those whose characteristics happen to match the demands of the new world. Sometimes it is a small omnivorous mammal. Sometimes an animal capable of eating almost nothing for months. Sometimes a bird finding seeds where green food has disappeared. Evolutionary success does not accumulate like armor. 100 million years of dominance provides no immunity against the next environmental change. In every crisis, the score begins again. Dinosaurs gained the world through one catastrophe and lost it during another. But their story did not end completely. It narrowed to a few surviving bird lineages that passed through darkness, cold, and hunger, and then began to expand again. The end of the Cretaceous is therefore not simply a story of disappearance. It is a moment of selection, after which one version of the world ended and another was given the chance to begin. Now we must draw one final boundary between the past that genuinely survives in the rocks and the past that we reconstruct. Without that boundary, any story about dinosaurs risks becoming either a collection of beautiful fantasies or the opposite extreme. The claim that we can know nothing with confidence. In fact, we can know a great deal. But different conclusions have different levels of reliability. The fossil record was never a complete chronicle of life. For an organism to become a fossil, an entire sequence of conditions must align. Its remains need to be buried rapidly and protected from scavengers, destruction, and transport by water. They must then survive the pressure of rock, chemical change, movement of Earth's crust, and millions of years of erosion. Finally, the right layer must reach the surface in exactly the place where a person will notice it. Most organisms do not pass even the first stage. Soft tissues decay, small bones are destroyed, and bodies are eaten. Animals that lived in dry mountains or forests were generally preserved less often than those whose remains entered river sediments, lake mud, or coastal deposits. The number of fossils discovered is therefore not equal to the true abundance of ancient animals. If many bones of one species are found in a region, that species may indeed have been common. But other explanations are possible. Its bones may have fossilized more readily. The region may have been studied more thoroughly, or the relevant rocks may simply be exposed at the surface. A rare fossil does not necessarily belong to a rare animal. This effect is known as taphonomic bias. Taphonomy examines everything that happens to an organism between death and discovery. It reminds us that the fossil record does not show the entire ancient world, but only the portion that passed through a severe filter of preservation. What then do we know directly? We can measure the shape of a preserved bone, see where muscles attached, and examine the structure of a tooth, eggshell, or skin impression. A trackway genuinely records the position of the foot and the sequence of steps. An embryo inside an egg confirms the egg's connection with a particular group. A healed fracture shows that the injury occurred during life and that the animal survived it. These are observable data, but even they require verification. A bone may be distorted by pressure from the surrounding rock. A footprint can spread in wet ground and become wider than the actual foot. A skeleton is sometimes assembled from several individuals found near one another. Before reconstructing anything, the researcher must therefore establish exactly what was preserved and how it changed after burial. The next level consists of conclusions we cannot observe directly, but can reconstruct with reasonable confidence. The structure of joints reveals the possible range of limb movement. Muscle attachment sites help estimate the forces acting on a bone. Teeth, wear marks, gut contents, and coprolites provide evidence of diet. Bone microstructure shows the rate of growth. Comparing numerous anatomical traits reconstructs evolutionary relationships. We have never observed the gait of a Tyrannosaurus, but its skeleton does not allow an unlimited range of possibilities. It could not move like a lizard with legs spread to the sides. The structure of its pelvis, knees, and feet rules that out. We never saw a sauropod digest food, yet its teeth, small head, and immense torso establish a fairly specific physiological picture. Such reconstructions remain models, but they are not arbitrary guesses. A sound model must simultaneously agree with anatomy, physics, movement traces, and comparison with living organisms. If it requires a joint to bend in an impossible direction, or a bone to withstand more force than calculations permit, it has to be rejected. The matter becomes more difficult when we turn to behavior. Parallel trackways may indicate animals moving together, but they do not reveal the organization of the group. Several nearby nests confirm the use of shared ground, but do not necessarily prove collective care of the young. An adult preserved on a clutch provides convincing evidence of brooding or egg protection. Yet we still do not know whether the family remained together after the young hatched. We may suppose that horns, crests, and elaborate plumage were used for display. Modern animals often employ conspicuous structures in mate selection, recognition of their own species, and territorial defense. But the precise courtship ritual of a dinosaur cannot be read from a single bone. This is where scientific language must retain words such as probably, possibly, and is consistent with. That is not a sign of weakness. It is an exact statement about the quality of the evidence. Finally, some details remain almost entirely unknown. The voices of most dinosaurs were not preserved. Exact color is known only in a small number of species, with exceptionally preserved feathers or skin. We cannot reconstruct the personality of an individual, its relationships within a group, or its response to a particular event. A single species may have included bold and cautious animals, experienced and inexperienced parents, dominant and subordinate individuals. Such individuality almost entirely disappears from the fossil record. Paleontology can reconstruct the biological possibilities of a species, but rarely restores a personal history. A detailed scene in which a dinosaur of a particular color makes a particular sound while defending its family in a precisely defined way, therefore inevitably contains artistic choices. It may be scientifically plausible if it does not contradict the data, but plausibility and established fact are not the same. The history of reconstruction shows clearly how this boundary moves. When the first incomplete iguanodon skeletons were found, a large spike was placed on the animal's nose. More complete discoveries later showed that it was a modified digit on the forelimb. Dinosaurs were long portrayed as heavy animals dragging their tails along the ground. Study of the spine and trackways raised the tail and completely changed the posture. Microscopic study of bone later changed our understanding of growth rates. Feather discoveries transformed the outward appearance of many theropods. Computed tomography allowed scientists to look inside skulls and bones without destroying them. Chemical analysis began to extract information about temperature, diet, and animal movement. The scientific image changes not because earlier researchers understood nothing. It changes because new material appears and old explanations are tested again. That is the normal operation of knowledge. Nor is a new reconstruction automatically better merely because it is new. A vivid image filled with feathers, complex social life, and unusual colors can also go beyond the evidence. A modern visual style is no substitute for scientific justification. A reliable reconstruction can always be separated mentally into layers. Here is a bone, direct observation. Here is the position of the joint, a well-founded anatomical conclusion. Here is the proposed musculature, a model tested by comparison with living animals. Here are the color of the skin and a specific expression of behavior, an artistically completed area where the data remain insufficient. The farther we move from the preserved object, the more important it becomes to state the level of confidence. But incomplete evidence does not make the ancient world inaccessible. A single bone tells us little. Hundreds of skeletons, tracks, eggs, pollen grains, sedimentary rocks, isotopes, and the results of biomechanical modeling create a remarkably dense network of evidence. We cannot see the Mesozoic in its entirety, but we can reconstruct its central processes: the movement of continents, changes in climate, the structure of food webs, animal growth, and major evolutionary transitions. The essential rule is not to demand from a piece of evidence what it does not contain. A feather impression proves the presence of a covering, but does not reveal the animal's voice. A clutch confirms reproduction, but does not describe the whole of family life. A track records movement, but does not necessarily explain its cause. A skeleton establishes anatomy, but cannot restore personality. That is where the boundary between fact and reconstruction lies. It is not fixed. Every new discovery may move it a little farther, turning a former hypothesis into a confident conclusion, or, conversely, revealing that a familiar image rested on foundations that were too weak. And yet, one of the most important reconstructions has now become a fact confirmed by anatomy and evolutionary relationships. The age of dinosaurs ended for non-avian forms, but the lineage itself did not disappear. When a bird lands outside the window, then, we are not seeing a distant relative of the dinosaurs or a faint reminder of a long-lost world. We are looking at a living branch of the dinosaurs themselves, the result of a history that began more than 200 million years ago and continues at this very moment. Our story has now come to an end. I hope this wonderful journey into the age of dinosaurs helped you relax, let go of everything that was troubling you, and fall asleep. Good night, and until we meet again.